Welcome back, everyone. I am pleased to introduce our next speaker, Robertson from Colgate University, and he will talk about the thread of Ramsey theory in Zeilberger's work.
Thank you. So I am honored to speak at this celebration. This talk will be different than many, and you'll see why. So first, why am I doing this? So when I was Doron is my PhD advisor while I was at Temple University, and for whatever reason, he gave me a problem in Ramsey theory, which was much different than what his other graduate students were getting. And I've always wondered why I got such a different type of problem. And so I decided to go through his articles and see if I can figure out how this came to be. So these are some of the papers. Well, these are the papers I'm going to be looking at. So he started his research life doing partial differential, or no, not differential, difference equations, but quickly moved away from that. And these are papers that have some kind of tangential relationship to Ramsey theory, except for the last one in 1998, which is the paper I did with him that was part of my dissertation. So as mentioned in the last talk, he is famous for his opinions, and here is one of them. And so I decided to take this advice. And in particular, I'm not going to mention any of my own results. And I'm just going through his paper and how they relate to what I do, which is Ramsey theory. So we'll start with some comments on Rotas Umbral calculus. So
you are aware that the slides are not shifting, yes?
They're not showing? Oh, okay.
You're on the first slide.
They are not moving.
They're not moving.
The solution is unshare and share again.
Okay. Are they moving now?
Yes.
Yes.
Okay. Sorry about that.
Okay.
So introduction.
But it's very small. It's very small now.
It's very small.
So why don't you make it full screen?
Full screen.
It's full screen for me.
It's presentation mode.
So
Let's
it's
try
like
this.
it's better. Yeah.
Okay.
Is that full screen?
No, but bigger than it was.
Not yet full. Almost full.
It's good now. It's good now, Aaron.
Okay, it's
It's
fine.
good
Okay.
now.
Anyway, we saw only the first slide.
You saw only the full slide. Okay, so come on. Okay. So this is what I'll be covering. So he started with
No,
partial.
Aaron, it's still small.
Still small.
It's small again. I don't know.
Okay. How's that?
Good.
That's
fine.
good.
This is good. This is good, Aaron.
Okay.
Yeah.
Okay. Sorry about that. So on the left in the 70s, he started with partial difference equations. And in 1998, that's his first explicit paper in Ramsey theory. And I always wondered how this paper came to be. And because he doesn't do Ramsey theory. And so I wondered. And so here is one of his opinions. So this is just giving a general talk. And in particular, at the end, you'll see you don't have to mention your own results. And so I'm not going to. So this is about going through his papers and seeing if I can figure out where this Ramsey theory problem came from. So comments on Rotas umbral calculus. So this is kind of magical how you can go from subscripts to superscripts. And the shift operator is at the heart of this. And in this paper, he also discusses the relationship with Fourier analysis. And the connection, I'm going to start with Summer80s Theorem. And so if we take any subset with positive upper density, it actually can be weaker. It can be Banach upper density. Then A contains arbitrarily long arithmetic progressions. And the one way to prove it is through ergodic theory. And here we'll see that T is the shift operator. And we're looking at a probability space now, and A is a measurable set with positive measure. Then this intersection has positive measure. We just need it to be non-empty. And so what this says is that A minus D, A minus 2D, A minus 3D are all in A. And Gowers uses Fourier analysis, similar tools here, but he developed new tools to give a new proof, which significantly improves the upper bound for these minimal numbers that we are guaranteed to have k-term arithmetic progressions. So the next result, direct combinatorial proof of a positivity result. So co-authored with Gillis, and here is what the paper is about. So each of 4 types of hats. And so there's no mention of colors in here, but what is really going on is we are coloring people. So we have n people. It's more likely that when I redistribute the hats, that an even number are incorrect than an odd number. And so we've got this 4 coloring and different behavior between even and odd. If we had the same number of each type of hat, we would have an equinumerous 4 coloring. And so there is a result by Conlin, Jungic, and Radojcic. If I have an equinumerous 4 coloring of 1 through n, there's no 4-term arithmetic progression that has all 4 colors. That's not guaranteed. However, if we have 3 colors, so an odd number here, we do guarantee what's called a rainbow 3-term arithmetic progression. So we see this distinction here. And this also brings in something that I'll mention later, which is the canonical van der Waerden theorem. So if I have a finite number of colors, van der Waerden theorem guarantees arbitrarily long monochromatic arithmetic progressions. However, if I use infinitely many colors, I don't have that guarantee anymore, but I can guarantee that it's a rainbow arithmetic progression. Okay, so the next thread I found was in how he says he views matrices. So not as linear transformations, but as weights of graph edges. So if you're familiar with Ramsey theory, this one should be pretty familiar. So in this paper, he used two types of edges. So the edges have two particular colors. So this is the famous Ramsey's theorem, that if I have enough vertices and I color each edge with one of our colors, then if I have enough vertices, there's some monochromatic complete subgraph. And so I'll look at the simplest case, two colors, and I want a monochromatic K3, so triangle. So 6 vertices. If I just randomly color some of the edges white, some of them black, you'll see that not all the edges are there yet, but there's no monochromatic triangle. But if I attempt to color the edge between 4 and 6, then either 1, 4, 6 is a black triangle, or 3, 4, 6 is a white triangle. And so this is the simplest case. Now, in terms of what was done in the paper, there were 2 types of edges in matrices. And so instead of using numbers, I've just have these types. And what we're looking for are actually patterns inside of the matrix. So that question mark here is the gray edge. So regardless of what you color it, if you color it black, then the corners of this blue triangle are all black. And if you color it, I'll say white, corners of the red triangle are all white. And then we move on. Here we have colorings in the paper itself. And looking at it as set partitions, which in Ramsey theory, the colorings are set partitions. And he works with signed permutations. So we've got 2 colorings of permutations. This is a very interesting result from Nogalone, that if you do permutation patterns, which I did a couple of papers early on, this combines the 2. So we've got Ramsey's theorem says that we have these monochromatic complete subgraphs. Alone's result says that we can take the vertices so that the difference between consecutive vertices follows any permutation pattern you want. And so it actually combines those 2, which I think is a very interesting result. So the Goliath theorem is actually a multi-dimensional Ramsey theorem. So we have a finite set in m-dimensional lattice. Then if we color the points between -n and n with m dimensions, we get some translated dilation of the set being monochromatic. And so this theorem is also used to prove that canonical van der Waerden theorem I mentioned earlier. Okay, so now we get to enumerating totally clean words. So he looks at generating functions over a finite alphabet that do not contain subsequences of what he calls forbidden words. And the connection is the Hales-Jewett theorem, which is a longer statement. So if capital W of M is the set of variable words, so by a variable word, I'm looking at a word that has the variable X in it. So something like 1, 2X is a variable word, but if there's no X, it's not. So if I look at the variable words, then there's some minimal positive integer, capital H, and this is a dimension. So such that for every dimension of at least capital H, and I'm coloring these. So these elements in here are words of length h. There's some variable word where if I plug in the integers 1 through k, w of I is monochromatic. So if I plug in 1 here, I get 1, 2, 1 is, say, red. If I plug in 2, I get 1, 2, 2 is also red, etc. And so, for example, if we look at the easiest case of this, word alphabet is 1, 2, length is R, and I'm using R colors. So if I consider just these R+1 words at the top, the pigeonhole principle says I have at least 2 the same color. And so I have a variable word where it starts with 1s, ends with 2s, all x's between some number of x's, where W of 1 and W of 2 have the same color by the pigeonhole principle. So the original motivation for this was multi-dimensional tic-tac-toe. And so that's just a side note. Next paper I found was on exact covering sequences. So I remember him lecturing about this in grad school. So we're looking at infinite arithmetic progressions that cover the integers exactly. So we don't want any intersection. The conjecture is that if I have these, what I'm calling the common difference is the modulus. If I have a set of moduli that the reciprocals sum to 1, then there exists an exact covering system with those moduli, if and only if, and then there's this specific p+1 coloring of the moduli and for every prime. So it's there are many criteria on this coloring. And Doron provided, we know that the moduli can't be distinct, and Zeilberger provides many counterexamples to this conjecture. And the connection is that if I have these infinite arithmetic progressions, it gives me a well-defined coloring of the integers. And if I look at this in reverse, Van der Waerden's theorem tells me that I have arbitrarily long arithmetic progressions of the same color, but I don't necessarily have infinite ones. So for example, if I take intervals alternating in color that just double every time, then whatever modulus you give me, it's between 2 to the n minus 1 and 2 to the n for some n. And so one of the next two terms, once it hits that block of 2 to the n, one of the next two terms is not going to be the same color. Okay. Then there's the Talmudic lattice path counting. So counting paths from the origin to AB. And the idea here is what is done with those that land on the line, and what is a fair way to count this. And this one is, it's not a big result in Ramsey theory, but the proof that is used uses partial sums of sequences. And I've always liked this one. If I have any A1 through AN integers, there's always a subsequence whose sum's divisible by n. So what we do is we take the partial sums up to the ith term. So this is similar to what's done in that paper. And if we assume none of them are divisible by n, then two of them are congruent mod n, so that their difference is divisible by n, and we have our answer. So we can actually take the subsequence to be at consecutive terms in there. So there's some consecutive terms that are divisible by n when we sum them. So this is from the area of zero-sum Ramsey theory. So we get to the Dinitz conjecture. This is starting to feel much more like Ramsey theory, less tangential. And this one is, we're looking at the complete bipartite graph, and the edges are allowed to have one of n colors. And the question is, can we always find a color assignment where no two edges that share a vertex get the same color? So we're looking at, again, some kind of Ramsey or rainbow Ramsey idea. And this is actually the first explicit mention of coloring. So we're getting much closer to Ramsey theory. So what's actually being asked is there a proper coloring in this? And rainbow Ramsey theory started historically as anti-Ramsey. So Ramsey theory, we know that there's monochromatic structures that are guaranteed. And the question was asked, well, what's the maximal number of colors that I violate that guarantee? And so the restriction to a proper coloring here makes it more difficult. But if you think of this, and this, I don't know, this probably been done somewhere, but if we take the star graph, which looks like this over here, and inflate it so that each of the vertices gets n independent vertices, what we're looking for is a proper coloring rainbow k sub n n. And then we finally come to the paper that was part of my dissertation. So these Shor triples mentioned here are just two integers and their sum. So it's the, if you're familiar with sum sets, it's the smallest case. And I assume, but I don't know for sure, that he got this from a conference where Ron Graham provided the question. And this is the first explicit Ramsey theory paper, and he's had a few since then, but that's what I found from going through all of his papers. Thanks.
Thanks a lot, Aaron. Thanks a lot. Question to Aaron?
Yeah, I want to add a word. Aaron just published a great book that I strongly recommend called Fundamentals of Ramsey Theory. And I would have loved this book so much, even if it would not have been dedicated to me. But to my great delight and beautiful surprise, it's dedicated to myself. But I would have even, it's such a beautiful book with really, really motivated explanations. So I strongly recommend that you buy this beautiful book, Fundamentals of Ramsey Theory, written by Aaron Robertson. Thank you.
Well, thank you, and happy birthday.
Thank you. It was a great book. Thanks so much. And one quick comment, the conference that Aaron mentioned was beautifully organized by Bill Chen, that I hope is here Bill Shen was the organizer in Tianjin. The first time I came to China was a great conference, and that's how I learned about this conjecture of Ron Graham. Thank you.
Thank you for mentioning it.
It was a great conference. And thanks to you, Bill. Without this conference, I would never have heard about this conjecture. Thank you.
Happy birthday.
Thank you.
Thank you. Any other comments? If not, let us thank Aaron again. Well, and we'll